Welcome to this lecture series in real analysis. In this lecture, we'll talk about monotone functions and let us recall something that we need. So we will only recall the intermediate value theorem. What does it say? It says that, well, the most general way I can express this is by saying that suppose we have a continuous function on an interval, then the image of the function is also an interval. And the more practical way of looking at it is the following. If the function takes two values a and b, so suppose we are trying to draw the graph of the function, and p and q are in the domain, meaning p and q are in the interval I, and the function takes, let's say, value a at the point p and the value b at the point q, then the function also assumes every value between a and b. Okay? So every value between a and b is achieved somewhere within this region. Okay, so that's the intermediate value theorem, and let us proceed. Here are some problems for practice. And now let us get started. So just give me 1 second. Yeah. So let's get started. So we need to make a few definitions. Fix a function from a subset S of reals to the real numbers. We say f is an increasing function if, well, graphically, it should be something like that, meaning it shouldn't ever come down. If it has achieved a certain value, then in the future, it should not achieve a value that is smaller than the value it has already achieved at any given time. So that's the kind of thing that we want to define. Here, of course, when we draw a graph, we can only draw it when S is a nice set, but the definition does not demand any niceness on S. So the most formal way of expressing it is the following. We say f is increasing if fx is less than equal to fy whenever, or let me say if, I don't want to use two ifs. So we say f is increasing if fx is less than fx is less than fy whenever x and y are in S and x is less than equal to y. So it is preserving the order on S. That's one way to say it. Fine, so that's an increasing function. And if you want to draw the graph, you can maybe, this is an example. Whoops. This is an example. Whoops. Doesn't matter. So there are infinitely many examples you can draw. So that is one example of an increasing function. And it can also become constant for some time. That's also fine, because we are not asking for the value to strictly increase. Even if x is strictly less than y, we do not demand that fx is strictly less than f of y. We don't demand that. Okay? But if you want to demand that, you will have to qualify with this word strictly. So we say f is strictly increasing if fx is strictly less than fy whenever x and y are in the domain and x is less than y. So that's a strictly increasing function, and one example would be something like that. All right. Similarly, you can fill what is meant by a decreasing function and what is meant by a strictly decreasing function. And we say that f is monotone if f is either increasing or decreasing. And you can fill in the definition for strictly monotone, which is to say that the function is either strictly increasing or strictly decreasing. Okay. And before we look at examples of monotone functions, we've already seen at least some examples of a monotone function. Recall, we have talked about monotone sequences. So if you think of a sequence as a function from naturals to reals, then an increasing sequence is precisely an increasing function of this sort. So the set of naturals become the set S here. So this is a generalization of the notion of increasing sequence, decreasing sequence, monotone sequence, etc. Okay, so we are just generalizing that notion. All right, so let's look at some examples. This function is not monotone, right? This is not monotone because it takes, or let me just draw the graph. I'm sure you can formally justify why, but if you want to draw the graph, the graph looks something like that. And if you take these 2 points, basically what I'm saying is you take these 2 points, these witness that the function cannot be increasing because the value comes down. And you take these 2 points, they witness that the function cannot be decreasing because the value goes up. So it's neither increasing nor decreasing, and hence it's not a monotone function. All right, but let me also say that this function, if you take this function, whose description is the same, this is an increasing function. This is an increasing function. Even though the description is the same, the domain has changed. So when we talk about increasing or decreasing functions, the domain matters. Okay? And this function is strictly decreasing. So remember that the graph looks like that. We are only talking about positive reals. The graph looks like that, and it is a decreasing, strictly decreasing function. As you increase the value of x, you decrease the output. So this is a strictly decreasing function. You can formally justify it. Okay? Now here is what we want to talk about. What about continuity? How does this notion relate with continuous functions? So fix an injective continuous function on a closed interval, a compact interval in fact. This is a compact set. We want to prove that f is strictly monotone, which means it is either strictly increasing or strictly decreasing. Okay, and here is, we are kind of trying to explain the thing graphically, but we would like to write a formal proof. Maybe I will, maybe I won't. Let's see if it is needed. So there are 2 cases. One case is that this will happen, or the reverse. Equality is not possible because of injectivity. So we are assuming this. The reverse or the other case is just an analog of this one. If you can prove strict monotone under this assumption, you can prove strict monotone under this occurrence. So assume this is the case, and we want to argue that the function is strictly increasing, right? So we want to argue that the function is strictly increasing, and let me maybe draw just some reference value. So let's say that is the point on the graph of the function corresponding to A, and it's better to have some extensions. Okay, so those are the values the function takes on A and B. Never mind. Okay, and we claim that if we choose 2 points in A and B, then to choose 2 points in A and B such that we will show that and once we do this, we will have proven strict increasingness of the function f. Okay, so let's say x is somewhere here and y is somewhere there. All right, so let's justify this. Why is this the case? And I don't want to write down things. Suppose not. Suppose this were not the case, then fx would be strictly less than fa because of injectivity. Equality is not possible. So the other possibility is this. So let's say fx is somewhere there. But by intermediate value theorem, the function would assume all possible values between this and that. And the function would also, so it would assume all possible between this value and that value within this interval. And it would also assume all possible values between this and that within that interval. But then if you draw this kind of a horizontal line, it is clear that this value will be achieved 2 times. Once in this interval, once in that interval, and hence the function wouldn't be injective anymore. So to just explain it once again, suppose fx is like that, somewhere there, then by the continuity of the function would look something like this. Okay? And hence, if you draw any horizontal line, it would cut, any horizontal line which is below this and above that, it would cut the function at 2 points, and these 2 points would witness the non-injectivity of the function. The formal justification of all this will come from the intermediate value theorem, because by the intermediate value theorem, the function assumes all possible values between this and that within this interval. And similarly, it would assume all possible values between this and that within that interval. And hence you would find 2 points, 2 distinct points, where the function takes the same value, and that would be a contradiction. So that justifies this. You can formally write it down. I don't want to write it. It will be just an unnecessary mess. Similarly, we can justify that. So assuming we have proven that part, we can now proceed to show that fy is less than fx. So let's say fx is somewhere there. Yeah, so suppose we have already justified that fx is less than fb. We just talked about that. We can similarly talk about this. It's a very same proof. So now why should fy be greater than fx? Again, you assume otherwise, then fy would be somewhere there, and the same argument goes through. You would have non-injectivity. Okay, so you can justify this, and therefore the function is strictly monotone. All right. More generally, if we have an injective continuous function on an interval, so I is an interval, then the function is strictly monotone. Okay, and this is an exercise. We proved it for a compact interval, but this is true for any interval. Basically, suppose a and b were endpoints of the interval. If the interval is already this, then this is exactly the previous case. Now you can make 4 cases. Either the interval looks like that, or it looks like this, or it looks like that, or it could be something of that sort. So this diagram doesn't do it justice, but doesn't matter. You can justify for each case. Okay, so this is our main thing that I wanted to discuss in this lecture. And as usual, like, comment, share, subscribe, and I will see you next time.